We started out this section just talking about some general terms that we need for discussing polynomial functions. And so a polynomial function is just a collection of terms that looks something like this. So it looks kind of bizarre and unusual, but here's an example of a polynomial function p of x, which is equal to, well, let's just say 2x to the fourth power plus x to the third power minus 4x plus 1. So that's a polynomial. And you can see the degree of the polynomial is the highest, the largest exponent in the polynomial, and that's 4. So this polynomial has degree 4. A sub n is the leading term, the leading coefficient, I should say, the leading coefficient. So in this case, a sub n is 2. N is a non-negative integer, so n can be anything except 0 or a negative number. So all the n's are 1, 2, 3, 4, 5, and so on. The coefficients are these numbers in the a sub I numbers. So here we have a coefficient of 2, and here we have, of course, a coefficient of 1. Here we have a coefficient of negative 4, and that's called the constant term, and the constant term is 1. The leading term is the term in the front of the highest degree. So the leading term is 2x to the fourth power. So polynomial functions have graphs that are characteristic because they are polynomials. So they have no breaks. They have no holes. They're smooth. They don't have any sharp edges. So this first one's not a polynomial because there's a break. Polynomials aren't allowed to have breaks. This second one is not the graph of a polynomial because it's not smooth. It has sharp edges. But these last two are both smooth and continuous. So those are graphs that could be the graph of some polynomial function. So to sketch the graph of these functions using transformations, we're thinking of these as functions now. And so we want to graph x squared minus 4. That's the graph of x squared shifted shifted down 4 units. So the graph of x squared shifted down 4 units would mean that the y-intercept is negative 4. So we have that. Now we want to find the x-intercepts, and that means we set x squared minus 4 equal to 0. So x squared minus 4 equals 0 means that x squared equals 4, and so x equals plus or minus 2, taking the square root of both sides. So plus or minus 2 means 1, 2, 1, 2. So there are x-intercepts here and here. So the graph does something like this. It goes back up like that. So there's the graph of x squared minus 4. It's a shift down 4 units, a vertical shift down 4 units. Now q of x, which is x minus 4 squared, is a different kind of shift. Sorry about that. Q of x is a different kind of shift. Sorry about that. I don't know what I did there, but anyway, q of x, x minus 4 squared. So this one is a shift in which direction? Well, x minus 4 is 0 if x equals 4. So it's a shift to the right, 1, 2, 3, 4 units. So we've changed the x-intercept. Instead of 0, 0, we have 4, 0. So that's the x-intercept. That's when x minus 4 squared equals 0. Now if we set x equal to 0, we get 0 minus 4 squared, which is 16. And so 16, let's just say, is here, that high. So that means that when x equals 0, y equals 16. So the graph has that for the y-intercept. X equals 0, y equals 16. And so the graph does something like, well, this 1, 2, 3, 4. So there's going to be another 16 units high point over here by symmetry of this parabola, which comes down, hits the x-axis, turns, goes back up. So there's the graph of that one. I will leave the next two to you, otherwise this video will get much too long. But this one is, first you're going to vertically stretch x squared. So what x squared normally looks like this. If you were to vertically stretch it by a factor of 2, it would actually make it look slimmer. So that would be the vertical stretch of 2 times, and then you would drop it 2 units. Drop it on the y-axis 2 units. So it's going from there to there, and that's how you would do that one. For 2 times x minus 2 squared, you would first have to do a shift of the x squared by 2 units to the right, and then you would stretch by a factor of 2. So it's going to shift 2 units this way and then stretch by a factor of 2. So it's, instead of being wide like the usual x squared, is going to be stretched again like that other one was. So similar kind of idea there. That led us to the discussion of end behavior of a polynomial function. And end behavior, remember, means that you're thinking about the x values approaching positive infinity or negative infinity. Remember, that means that x becomes large in the positive direction or x becomes large in the negative direction. And we found that there are basically four kinds of end behaviors of polynomials as the x values get large. The y values will approach either positive or negative infinity depending on the leading term of your polynomial. The leading term is the term that determines the end behavior. All the other terms are insignificant by comparison to the leading term when x is a very large number, either positive or negative. And so you can look at that term and decide whether your graph has one of the 4 different types of end behaviors. So one type of end behavior is the kind that as x approaches negative infinity, the y values approach negative infinity. But as x approaches positive infinity, the y values approach positive infinity. Now we don't know exactly what's happening in between here, how many times we cross an axis or whatever, but we do know that on the ends the graph looks like that. Now, if the coefficient is negative and the polynomial has odd degree, then this is just a reflected graph. So you have the opposite, reflected kind of end behavior. Now, if your polynomial has even degree, that means that as long as the coefficient is positive, the graph will have upward opening end behavior. But if it's even degree and the leading coefficient has a negative sign, then the graph will open down on both ends. So those are the 4 different types of end behaviors, and all you have to do is look at the leading term. So compare the leading term to the polynomial that has that same single leading term. So here you would compare to negative x to the 5th. Well, if x is a very large positive number, then x to the 5th power is also a very large positive number. But then you're going to take the opposite. Therefore, negative x to the 5th power is going to be approaching a very large negative value. Therefore, the end behavior on the positive side of the x-axis is to be pointing downward like this. The x's, remember, are going this way, and the y's are going up and down this way. Okay, so now, on the other hand, as the x's approach negative infinity, what happens to negative x to the 5th power? Well, if x is approaching a very large negative number, x to the 5th power is still a very large negative number, but then you do the opposite. Negative times that negative is going to be a positive. So that means that this is going to approach positive infinity. And so therefore, as the x's are growing large in the negative, I meant to put a negative symbol right there, negative direction, negative infinity. As x's approach negative infinity, negative x to the 5th approaches infinity. So the x's now are going this way. That means the y's are going up this way, and so your end behavior is like this on that end. So all you have to do is figure out what the intercepts are so you know what path the graph takes in between those two ends. So you can see how this would work here. You would compare the graph of p of x with the graph of q of x. And if you zoom out enough, you'll see that they both resemble the same graph. So 3x cubed will look like this, If you zoom out far enough, the other one will look very similar to it. It will almost coincide exactly with it. So you can experiment on your own. Some of this stuff is mostly just terminology. So looking at a polynomial function and its zeros, if you have a polynomial function and c is a real number, the following are all equivalent. If you say that c is a zero of p, it means the same thing as x equals c is a solution of the equation p of x equals 0. So, you know, you've been doing these quadratic equations all this time. You've been solving equations like f of x equals, I'll say x squared plus 4x plus 3. You've been solving equations like 0 equals x squared plus 4x plus 3. You know, by factoring or by completing the square or by using quadratic formula, but you've been doing this, and you're finding a solution of the equation p of x, in this case f of x, equals 0. Well, that's what we mean by a zero. So whatever your solutions of this are, and I think there are two. I think the solutions are x equals 3, or x equals negative 3. No, x equals 3, and x equals 1. Those are the two solutions. Well, we call those numbers 3 and 1. Those are zeros. Those are zeros of the polynomial f of x in this case. And then we can say x minus c is a factor of p of x. So you look at x equals 3, that means that x minus 3 is a factor. And you look at x plus 1, at x equals 1, and that means x minus 1 is a factor. And these are the factors of this function f of x. And indeed, you know that's true because that's how you solve this equation. You solve this equation by factoring that. And when you factor that, you do get this. And then you set each factor equal to 0, and that's how you get your zeros. And then finally, we know that the number c, which is the number that's the 0, is an x-intercept of the graph. We call it the x-coordinate or the x-intercept to be technically correct. Okay, well, that sort of leads to the intermediate value theorem, which is the theorem that tells us that if there are 2 points on the graph of your function where the y-coordinates are opposite sign, that means that there has to be at least 1 0 in between the two numbers a and b. So it just stands to reason that if you are down here on a graph of a smooth and continuous function, and then you wake up and you find yourself here, that means you had to have crossed, well, you had to have crossed a lot of horizontal lines, but in particular you had to cross this line right here. That's the only way you can get from here to here. You have to cross that line if you're going to follow this path, which you know is smooth and continuous. And so therefore that means that to get from this point to that point and travel this smooth continuous path at some place, since you're on opposite sides of this line, you have to cross that line to get to that point. And when you cross that line, that means that p of that number c is 0. Therefore, you know that there has to be at least one 0 if you know that two function values have opposite signs. You know there has to be at least 1 0 between them. So you're looking for something that's there, for one thing. See how we can make use of that theorem by looking at sketching the graphs of these polynomials. So the first thing you do is find the zeros of the polynomial. So we usually try to factor the polynomial to find the zeros. This one is already factored for us, and so we know what the zeros are. We just look at the factors. The zeros are the numbers x equal to 0 from this first factor, 3 from the second factor, and negative 2 from this third factor. So there are 3 zeros. Okay, then what I like to do is just go ahead and sketch the zeros. Sketch the zeros on my x-axis, 0, 3, and negative 2. So 0, 1, 2, 3, and 1, 2, negative 2. So that's a 0 at negative 2, that's a 0 at 0, and that's a 0 at 3. So here's the y-axis, goes through 0. Okay, then it says, do some test points. Make a table of values for the polynomial and include test points to determine whether the graph lies above or below the x-axis on the intervals determined by the zeros. Include the y-intercept in the table. Okay, the y-intercept is, what I'll do first, that's when x equals 0. So we're going to find y when x equals 0. So if x equals 0, well, no, that's not what the, yeah, that is what the y-intercept is. Oh, it's 0, 0, of course, because we know the x-intercept is at 0, 0. That means the y-intercept must be at 0, 0. Okay, so now we want to try numbers between -2 and 0. So let's try x equals -1 and see what we get for our function value. Our function is x times x minus 3 times x plus 2. If x is -1, that's going to be -1 times -1 minus 3 is -4 times -1 plus 2 is 1. So we get 4. So when x is -1, y is 4. So that means the graph is up here. I suppose I should do end behavior next. Now, next we want to take a number between 0 and 3, our next two zeros. I'm going to pick 1 because it's easy to calculate with 1. So our first factor, x, will be 1. Our next factor, 1 minus 3, is -2. Our next factor, 1 plus 2, is 3. So we get -6. So when x is 1, y is -6. So that means it's pretty low down here on the y-axis. I'll just go ahead and move up a bit here. Extend my y-axis, 2, 3, 4, 5, 6. So 1 goes down here to -6. Down there. Okay, now let's do the next thing, which is the end behavior. That's to determine the end behavior of the polynomial. Well, if you were to multiply this polynomial out, the leading term would be x to the third power. So this has the same end behavior as x to the third power, which means that it's going to -infinity when the x's are large negative numbers, and it's going to positive infinity when the x's are large positive numbers. So now we just have to think about how it crosses the x-axis. Well, we know that it's got to come up from -infinity, and it's got to cross the x-axis at -2. It's got to go all the way up to this point, maybe higher, I'm not sure, but then it's got to come back down, and it's got to go at least down to this point. It may go lower, we're not sure, but then it's got to come back up to 3, and then it continues upward forever. So there's your sketch of your graph, and it's really quite interesting and quite lovely. So let's see. I almost hate to erase it. It's so lovely. We'll just do the next one for you, so you can play that back whenever you want to. It's so lovely. Let's just erase all these things and clear up the space for our next example, which is p of x equals x cubed minus x squared minus 6. And that one's not in factored form, so always factor it. So we're going to factor out the x, and that'll give us x squared minus x minus 6. And I believe that can be further factored as x. Let's see. We have x. To get a -6, we need a -6. It's going to be a +2. Okay. So now we know the zeros. The zeros are 0, 3, and -2. So let's plot those out. 0 is a 0. 3 is a, oh, this is, you know what? This is exactly the same problem as that one. So I don't know why I did that. Now I remember we did that in class too, so we won't do this one because it's the same exact problem. That's pretty goofy. Alright, so we'll just go to the next problem. The next one is similar. There's a common factor of x squared. So we have equals x squared times, what is that? X squared minus 3x minus plus 2, which can be further factored as x squared times x. Let's see. Both minuses, a 1 and a 2. And so the zeros are 0, 1, and 2. Okay, so we're gonna find something out about this x squared and what the effect of that x squared is on the graph of this function. So let's plot out our zeros. 0, 1, and 2 are the zeros. 0, 1, and 2 are zeros. So we know the graph passes through those guys. Okay, so now we want to do test points. So we want to pick numbers between our zeros. So we're going to have at least two numbers, and we're also going to do the, well, we already know the x-intercept because the graph goes through 0, 0. So we're good with the x-intercept. So let's pick some numbers that are between our zeros. So between 0 and 1, we'll pick 1/2. And I like to use the factored form because that's usually easier. So 1/2 squared is 1/4. 1/2 minus 1 is -1/2. And 1/2 minus 2 is, let's see, 1 is 3.5. It's -3.5. -3.5 is -3/2. So I believe this is correct. So I get +3 over, 3 I said, over 16. The point is that it's positive. It's not real high up, but it's a positive value. So at 1/2, it's like maybe about this high. Now, when x is between 1 and 2, we might pick 3/2 for x. 3/2 for x. So now we're going to do 3/2 squared, which is 9/4. And 3/2 minus 1 is 1/2. So times 1/2. And 3/2 minus 2 is 3/2 minus 4/2 is -1/2. And so I get -9 over 16. And so -9 over 16, if here's -1 right here, -9 over 16 is it's probably a little bit more than half, so it's about maybe there. Now the end behavior for this polynomial function, which is of degree 4, it's of degree 4, it's the same as the end behavior of x to the 4th power. So the end behavior is up as x's go to -infinity, and up as x's become increasingly large in the positive direction, or go to positive infinity. So that means that the graph must do this. It goes through 0, but it's still positive, and then it comes up, and then it goes through 1, and then it becomes negative because it has to come down here, but then it has to go through 2, but then it never turns and comes back down again. It just continues upward forever. And so that's what the graph looks like. Looks like this hump might be a little bit lower than this hump. It's really hard to tell, but this is a pretty good approximate graph of that function. Okay, so the thing that was interesting about the graph of that function was its behavior near the 0 at the origin. Its behavior near the 0 at the origin was kind of like this. And you remember that the factored form of that had that factor of x squared. The x is squared, and so we say for this particular factor that we had a 0 of multiplicity 2. The multiplicity is the degree that is associated with a factor. So since this x was squared, we have a 0 at 0 of multiplicity 2. And 2 is an even number, and if m, the degree there, is even, then the graph does one of these two things near that 0. And so that's what happened with that graph. Well, let's look at another example of this type of behavior so that we can get a better understanding of it. So we'll look at the polynomial here, p of x, and we'll factor that by grouping, and so that's going to give us x cubed plus x squared. And in the second grouping, I'm going to factor out the negative because the x and the 1 both have a negative, but now it's x plus 1 in the parentheses. Now here I factor out an x squared. That's going to leave me with an x plus 1 minus an x plus 1. Now I have x plus 1 as a common factor, so I write x plus 1. And then here I wrote the x plus 1, so that's x squared. And then minus here I wrote the x plus 1, so that's 1. That's the other factor that's right there. And now this can be factored as x plus 1 times x minus 1. It's the difference of two squares. And then I'll rewrite this finally using an exponent to indicate that this factor is squared. So we say that we have two zeros, one is -1 and the other is 1. But this 0 is a 0 of multiplicity 2 because it appears from a factor that appears twice. So it's a 0 of multiplicity 2. And what that means, since this is even multiplicity, is that near this 0 on the x-axis, the graph looks like that. It has a sort of an upward concavity. So let's see what that means for the graph. We'll discuss the zeros and the end behaviors, and we'll make use of the fact that we have a 0 of even multiplicity to help us shape the graph. So this one, if you were to multiply, well, you don't have to multiply it out, it's already multiplied out for you here. We see it has the same behavior as x cubed. Let's get the zeros down. There's a 0 at -1, and then there's a 0 at 1, right? So, yeah, so we have that 0 and that 0. So here's the y-axis. All right, now the end behavior is the same as the end behavior of x cubed, so that means it goes upward this way, and it goes downward that way. There's your end behavior. Okay, and we know that at -1, it has to have behavior like this. So that means it has to do this. So there's something interesting going on here, because that's not what I expected. So hold on. Well, let's get the y-intercept first. The y-intercept is -1. We can get that from here. We just let x be 0 here in this polynomial. We get -1 for the y-intercept. So I know the graph goes through -1 here. Actually, I don't think the graph has to be like this, because remember there are two options. The graph could either be like this, a sort of concave upward, or it could be like this, sort of concave downward. So the option of concave downward must be the one we have here. So that means the graph comes up to here, comes back around, goes through -1, and then pops back up through 1, and then continues upward forever. So that's what I'm saying is the graph. Just remember that when the multiplicity is even, it could either have this upward concavity or this downward concavity as its characteristic of the graph. Okay, let's just do the last one. I'm going to erase all of this. I don't think we need any of these objects. Just say goodbye. And so now we'll look at this one. Now, if this one's already in factored form, which is good because you can easily identify the zeros. The zeros are 0, -2, and 3. And we notice that one of them, 3, is a 0 of multiplicity 2. So we're going to have one of these behaviors near where 3 is on the x-axis. So let's make use of that. So the zeros are at 0, 3, and -2. My 3 zeros. Okay, now we know that we have the end behavior to check next. Okay, so if we were to multiply this out, we would have an x cubed times an x, so that would give us an x to the 4th. If we multiply this out, there'd be an x squared in there, so we would have an x to the 4th times an x squared. So that's going to give us x to the 6th power. So this polynomial has the same end behavior as as x to the 6th power, which means that it goes upward over this way as the x's are large negative numbers, and it goes upward this way as the x's are large positive numbers. So it's got that upward concavity on the ends. So what happens to this graph? Well, let's put the y-axis in. Let's figure out what the y-intercept is. The y-intercept. What would the y-intercept be? If you set x equal to 0, you can find the y-intercept. Oh, well, if x equals 0, this equals 0. So there's your y-intercept right there. We already have it because it's the x-intercept. So we're ready to do the graph. The graph has to have, remember, one of these kinds of behaviors near 3. But we know that on this side of 3, the graph is always going upward. So that means on the other side of 3, it must be going upward as well. But it has to go through this point. So we probably should do an intermediate value for, say, x equals 1. So let's do that. If x equals 1, p of x is 1 cubed, which is 1, times 1 plus 2, 3. times 1 minus 3, which is negative 2, squared, which is 4, so it's 12. When x equals 1, you get all the way up to 12. Let's suppose this is where 12 is, right there. There's 12. So at 1, you're way up here at 12, so we're coming way up high. But at some point, we have to turn around and come back down because we have to go through the origin. Then we have to dip down and then turn. Now we should probably figure out p of negative 1. So if x is negative 1, x cubed is negative 1. Negative 1 plus 2 is 1. Negative 1 minus 3 is negative 4. And when you square that, you get 16. And so this is negative 16. So this is going to go way down to negative 16, which maybe that's where negative 16 is, because that's where 12 is. So it's, you know, a little bit further down. So there's negative 16. It's going to come all the way down, and maybe even go down lower, not sure. But at some point, it has to turn around and come back up because of the end behavior. So that's kind of like what the graph looks like. It swoops down this way, it comes up, and it goes through 0, and it goes high, and then it comes down, and it turns around at 3, and it pops back up forever. So there's your graph. So, when you're graphing polynomials, you're interested in the so-called extrema, which are the max and the min values of the polynomial function. The extrema are y values, they're function values, okay? That's what they are. Now, they occur at the value x, but if you're asked for the extrema, you're being asked for the y value. And if you think about it, if the polynomial has degree n, the most number of zeros it can have is n, so the most number of extrema it can have is n minus 1. So if you have a polynomial of degree 3, 1, 2, 3, and they're all of multiplicity 1, then how many extrema can you have? Well, if you have up to down, and then back up again, and then back down again, you have 2 extrema, one here and one here, and that's if you have degree 3. If you have degree 4, 1, 2, 3, 4, that's the most number of zeros you can have, and so you can come from the bottom and then you can go up and you can go down. This is the worst case scenario. The maximum amount of turning is 1, 2, 3. So you can see if the degree is n, then there are at most n minus 1 local extrema. We don't prove this, we just kind of accept this as true because it looks visually like we can show it's true for a couple of cases, and then we believe it. So that means that this polynomial right here, x cubed minus x squared minus x, will have at most 3 local extrema. Now we'll see what they are. So we have x cubed minus x squared minus x. We can factor out an x, and that gives us x squared minus minus x minus 1. I don't know why I got a little confused there. That's going to be, if I multiply it back out, I get it right. Okay. Now, I can't factor x squared minus x minus 1, so I'm going to have to solve for zeros by using the quadratic formula. So, let's do that. We'll use the quadratic formula. And remember, the quadratic formula tells you, sorry about that, that your x is equal to the opposite of b plus or minus the square root of b squared minus 4ac, all of that under the square root, and both of these over 2a. And so what does that become here? That becomes the opposite of b. B is negative 1, so that's 1, plus or minus the square root of b squared, which is 1, minus 4ac. 4 times a is 1, times c, which is negative 1. So I need that. I don't need the 1, though. And that's over 2a, which is 2. Now, 1 minus 4 times negative 1 is going to give you 5. So x is equal to 1 plus or minus the square root of 5 over 2. Now, that's two numbers, and those are real numbers. And so that means we can factor this, because remember, if c is a 0, then x minus c is a factor. And so here, we can factor this in the following way. X times x minus 1 plus the square root of 5 over 2. 1 plus square root of 5 over 2, because 1 plus the square root of 5 over 2 is a c number, so x minus that c number is a factor. And the other factor is x minus 1 minus the square root of 5 over 2. So we have 3 factors because we have a polynomial of degree 3. That's the maximum number of factors we can have. So we can we have actually done something that we weren't asked to do. We were just asked to graph the polynomial. Oh, okay, well we have to do this to graph the polynomial. Actually, we can graph the polynomial, just use your calculator to graph it. And then when you're done graphing it, what you'll do is you'll access the second function of the trace button, because that's calc. So the second function of the trace button, which is calc. And then you will choose either the option and choose the one that's correct for where you are on the graph. So if you're looking for a local max, make sure that you choose the function that says maximum. And then you can follow those instructions. And if you're looking for a low point, the y-coordinate of low point, and the x-coordinate as well, then use minimum. Okay, so just remember that the local max and the local min are the y values. So you have x, and then you have max. Okay? Or you have x, and then min. The min and the max are the y values. So the most common error is when students are asked what's the maximum or what's the minimum, they report the value of x because we're accustomed to solving for x. Maybe that's why, I don't know. But if you're asked what's the maximum or what's the minimum, that means you're supposed to tell me the y value, not the x value.